record. Well, hello everyone. My name is Parni Angane, and I'm gonna talk about a paper titled Physics-Informed Neural Networks, which is a deep learning framework. This paper is an interesting paper because the authors try to combine two kinds of models, neural networks and physics-based models, which both of them has some advantages and disadvantages, and the combination of them can improve their performance. First of all, we should know why we use neural networks, because their ability to learn complex patterns, their flexibility, their ability in parallel processing, their ability in generalization, end-to-end learning, and so on. But the neural networks have some disadvantages too. For example, they are doing well in just complex problems, but in simple problems, they cannot do well. They need lots of data. Their computation and resource requirements is a limitation for them. And also in real world, we do not have enough labeled data to train them. And the domain knowledge and feature engineering is among the limitation of neural networks. About the physics-based models, also they have some advantage. For example, they express the fundamental laws of the problem. They can model the dynamic behavior of the problems and variables. They can capture conservation principles, for example, conservation of mass and momentum conservation. They can consider these conservations. They can describe the complex relationship between variables. They can predict and analyzes also the behavior of the system. But the physics-based models have some disadvantages too. For example, they are limited to the known physical laws and principles. They require accurate and complete data for parameter estimation and calibration. They rely on simplifying assumptions to make the mathematics tractable, and they have difficulty in capturing complex interactions or nonlinear behaviors. They struggle to adapt or generalize to different scenarios or new data, and one of the most important limitation of them is that they are computationally intensive. But the combination of neural networks and physics-based models can take the advantage of both of those models and construct a high-performance model for conditions that we do not have enough data and the problem is complex. The neural network can handle the complexity and nonlinearity, and the physics-based and putting physics in the neural network can limit the neural network to don't drive the training algorithm to the space that we do not have a physical interpretation for them. Physics-informed neural networks have some advantage. For example, as I mentioned, incorporation of domain knowledge, improved in interpretability. They are data efficient, and their generalization and also their combination of neural networks and physics models can improve the both of these models if we just run them individually. Related works to use the combination of physics-based models and neural networks and machine learning tools. We can mention the work of Wang et al. That they developed a physics-informed machine learning algorithm for modeling the turbulence problems. And also in 2016, Ling et al. Identified the regions with high Reynolds averaged Navier-Stokes uncertainty using the combination of machine learning and physics-based models. And also in 2017, H et al. Used a recurrent neural network to learn the reactions and responses of the data, which were imposed to the discretized ordinary differential equations. And in 2022, Nazari et al. Developed 3 architectures of a deep learning model for a parameter identification of the Saint-Venant equation, which is the physics model to model the flow rate in an open channel. Here you can see the instruction and the construction of the physics-informed neural network. The most important part of the physics-informed neural networks are their loss function, which include 2 parts, 2 terms, MSE sub u, which is the typical and regular loss function of any neural network, is the difference between the prediction of the neural network and the observation data. The important term here is the MSE sub p, which is a mean squared error of the regularization term that we put the physics of the problem in the loss function to be minimized using neural network, that the model consider the physics while it is capturing the complexity by neural network. In this study, authors used 2 types of physics-informed neural networks. The first one is discrete time physics-informed neural network, and the second one is continuous time physics-informed neural network. You can see the defined loss function for both of these models. And they used 2 experiments, 2 equations, 2 physical equations and models to do their physics-informed neural network. The first experiment is using Cartwright, the Varese as KdV equation. This equation is a partial differential equation that includes and that considers the propagation of long, weakly nonlinear and dispersive fluid waves in 1 dimension. And it represents the temporal change of the wave amplitude and also advection and dispersion terms in it. The second experiment of this study is Schrödinger equation. Schrödinger equation is a fundamental equation in quantum mechanics that describes the behavior of quantum particles. It includes the Planck's constant, also time and the wave function of the particle, and another term as a Laplacian operator which is representing the special second derivative, and here V is the potential energy function acting on a particle, and I is the imaginary unit. What I have done in this project are summarized here. And first of all, I obtained the main code, which was for physics-informed neural network in the GitHub of the authors of this paper. I cited the paper in the first slide of my presentation. You can find it there. And first of all, their code was based on TensorFlow 1, but the recent TensorFlow is TensorFlow 2, and I had to revise the code and change the comments to be run on TensorFlow 2 library in Python. And then when I solved the errors, I tried different experiments, and I optimized the performance of the code by fine-tuning some parameters such as epoch size, iteration count, and the maximum and minimum value associated with the optimization algorithm. The optimization algorithm here was LBGF, and also I added the some different percentages of noises to the training data to assess the performance of the models with different noises. The authors just used 1% of noises. Here you can see the results for the physics-informed neural network based on KDV. The neural network architecture for the first experiment, which is modeling the KDV partial differential equation. To solve the KDV partial differential equation, I used 4 hidden layers with 50 nodes in each layer. As you can see here, I have a screenshot. I put the screenshot of my terminal when I was running the code. You can see the results and error for the lambda sub 1 and lambda sub 2, which are the unknown parameters of the KDV equation. These architectures did a great job, and using 2% of noises, again, there is a reasonable and it's acceptable amount of error. And the right figure is showing the exact solution for the KDV equation in 2 different locations, as you can see here. And the other 2 figures are details of the exact solution in different snapshots, t equal to 0.2 and in t equal to 0.8. You can see here, although there are different complexity, and there is different complexity between these 2 snapshots, but the model could appropriately and efficiently capture the nonlinearity in different snapshots. Here you can see the results for the second experiment using Schrödinger equation, partial differential equation in a continuous time model. Here, the architecture of neural network is 5 hidden layers with 100 nodes in each layer. Again, you can see that the model could capture the nonlinearity and the complexity between different snapshots, and the errors of unknown parameters are acceptable, and it did a great job again in the second experiment. About the lessons that I have learned from this project, I can say that I learned how to work with deep learning models, how to implement them, and how to find out line by line deep learning code, how is working. And also I used physical informed neural network to solve the partial differential equations for 2 experiments. Which was really helpful for my insight about the combination of neural network and physics-based models. And I hope that I can use them in my future studies. But I have some questions that I'm looking for getting their answers in the future. First of all, I can ask, why does the algorithm convert to unique values for the parameters of the differential operators? And could this be mitigated by using different activation functions? Also, another question can be, are the mean square error and the sum of squared errors the appropriate loss functions? And in this study also, I used how to convert the commands of TensorFlow 1 to TensorFlow 2, because there are lots of codes that are based on TensorFlow 1, which now is not available, and it is just for example, Conda is providing TensorFlow 2. And although we can use TensorFlow 1 and install it, but there may be some problems. And also, I learned how to solve partial differential equations. I've learned how physics-informed machine learning models works, and and another lesson that I learned from this project was that the requirement of employing a large number of collocation points to enforce physics-informed constraints across the spatiotemporal domain can lead to decrease in the efficiency of continuous time modeling using physics-informed neural networks. And in conclusion, I can say that physics-aware neural networks serve as a novel types of function approximators that have the ability to represent the physical laws underlying a given dataset. These networks are modeled using partial differential equations, and the aim of this study was to develop database algorithms that can predict solutions to nonlinear partial differential equations. And as deep learning technology is continuing to grow, both in terms of methodological and algorithmic developments, I believe that this is a timely contribution that can benefit practitioners across a wide range of scientific domains. Also, specific applications that can readily enjoy these benefits include, but are not limited to, data-driven forecasting of physical processes, model predictive control, multi-physics, multi-scale modeling, and simulation. And finally, the authors of this study believe that this research promotes a productive collaboration between machine learning and classical computational physics based on mathematical models, which has the potential to enhance both disciplines and result in groundbreaking advancements. Thank you for your attention.